Hello students, how are you all? I hope you are all very fine. So today let's start with some numericals based on the topics which we have already done. So basically we'll concentrate on some additional numericals based on calculating the capacitance, right? So we'll start with these three examples first. So let's consider on the first question. The question is, these are the plates all identical, each of area A, and the separation between the plates is given to be same, which is given to be small d. This is the plate separation. So all the plates are identical. This one is the arrangement, that is first one A, and this is the second, that is B. Each plate is having the same cross section area, capital A, and the gap or the separation is given to be same, each being equal to small d. We are supposed to find out the net capacitance between the points A and B. So let's start with the first one. So this is to be determined. The net capacitance between the points A and B is to be determined. So how to proceed? Net capacitance between the points A and B is to be determined, means the potential difference is to be applied across A and B. Now look. Suppose it is a higher potential and let us consider this to be a lower potential, right? So, since the entire arrangement is connected to higher potential, therefore it will be at higher potential, it will be also at higher potential. While on the other hand, B is connected to this particular arrangement. So accordingly, since B is at lower potential, therefore this must be at lower potential and this must be also at lower potential. Now you can do the numbering 1, 2, 3, 4, suppose. So, it is equivalent to this particular diagram basically. Look, the above diagram can be redrawn in this particular manner. 1, 2, it will act as a capacitor, 2, 3 will act as a capacitor, and 3, 4 will also act as a capacitor. Students, in a capacitor, it consists of two equal and opposite charged plates having equal and opposite surface charge densities, isn't it? So, 1, 2 it will act as a capacitor, 2, 3 will act as another capacitor, and 3, 4 will act as another capacitor. So, the equivalent diagram of this particular given arrangement can be redrawn in this particular manner. It is equivalent to actually 3 capacitors connected in parallel. I'll convince you. Suppose this is point A and this is point B. Now A is connected to 1 and 2, right? 1 and 3 basically. 1 and 3 are at higher potential. Suppose this is 1, this is 3. Now B, it is at lower potential, connected to 2 and 4. This will be 2 and this will be 4, right? Over here, you can consider 2, 3 case as well. So this is 3 and this is 2. So basically, this arrangement can be converted into this simple circuit. This is at higher potential, so plate 1, plate 3 and plate 3, they are at higher potential. Point B is given lower potential, so they are at lower potential. 2 and 4. 2 and 4 are at lower potential, 1 and 3 plates are at higher potential. So students, basically it is equivalent to the circuit comprising of 3 identical capacitors all connected in parallel. The plates of each of these capacitors are connected between the same 2 points A and B. So this is equivalent to a circuit comprising of 3 capacitors connected in parallel. Now what is the capacitance of each capacitor? It is epsilon A by D. This is the formula for a parallel plate capacitor, the capacitance of a parallel plate capacitor. All the 3 capacitors are of same capacitance. So what about net? It will be C plus C plus C. Make use of the formula. As per the law of parallel combination of capacitors, the equivalent capacitance is given by this particular formula. So we get 3C. So it will be equal to 3 epsilon A by D. So this will be the answer. I hope it's pretty clear. So it is actually the combination of 3 capacitors connected in parallel, right? Let's proceed to the second one. Let's proceed with this. We'll approach this question also similar to that of the previous one. Now a source is connected between A and B. Means one must be at higher potential, the other must be at lower potential. Let us assume A to be at higher potential, B to be at lower potential. So this one will be at higher potential. Sorry, this one will be at lower potential and this one will be at lower potential. It's connected to B. This arrangement is connected to B. Now this arrangement is connected to A. Therefore this will be at higher potential. This one will be also at higher potential. And here also the plate area each is given to be A and the separation each is given to be D. It's already given in the question. The gap between each of them is given to be D, while the area of each of the plates is given to be A. Right? So again we can number it 1, 2, 3 and 4. Now look, a capacitor is composed of two plates which should have equal and opposite surface charge densities. 1, 2, this will act as a capacitor. 3, 4 will also act as a capacitor. 2, 3 won't act as a capacitor. So it is equivalent to two capacitors connected in parallel like this, A and B. It is given higher potential, it is given lower potential. So this will be at higher potential, this will be at lower potential. Now 2, 3, this is 2, this is 3. Lower potential B. So this one and this one, 1 and 4 will be at lower potential like this. So students, this arrangement is equivalent to two identical capacitors connected in parallel. The capacitance of each of the parallel capacitors is epsilon A by D. Therefore, over here again, since they are connected in parallel, therefore using law of parallel grouping of capacitors, we get C net equals to C1 plus C2. That is twice C, and it is equal to twice epsilon A by D. This will be the answer. So this is the equivalent to the three capacitors connected in parallel, while this circuit is equivalent to two capacitors connected in parallel. Right? One more thing. If it's given like this is suppose A and this is a single plate and it is connected to a wire which is maintained, whose end is maintained at potential B. Or this can be considered to be A and this can be considered to be B. And the separation between the plates is given to be D and cross-section area of each plate is given to be A. What will be the equivalent capacitance in this case? Now students, it is equivalent to the same thing. Why I will convince you. Suppose it is at higher potential and this is at lower potential. So point A is at higher potential. So this plate connected to point A will be at higher potential. While point B is connected to this arrangement. So it will be at lower potential, it will be also at lower potential. Right? So what to do is, suppose it is 1, this is 2 and this is 3. 1, 2 and 3, 2. It will act as capacitor. So it is also equivalent to two capacitors connected in parallel like this. Suppose this is point A, this is point B. Point A is at higher potential. This is 2. Point B is at lower potential at 1 and 3. So 2, 1 and 2, 3. These are acting as two capacitors connected in parallel. So again we will get the same thing. C net would be given by C1 plus C2. And each capacitor is having capacitance of epsilon A by D. So since they are connected in parallel, so it will be C plus C, that is twice C. So here also the answer is twice epsilon A by D. So students, do remember, whether it's this case, the conductors are arranged in this particular manner or this manner, both are representing the same situation of two capacitors or conductors connected in parallel. So in both this scenario, the net capacitance would be twice epsilon naught A by D. So I hope such questions can be easily attempted by using this particular concept, right? Let's consider the third one. It's an interesting one, an important one too. It's a capacitor. One plate is in the form of a plain horizontal sheet, right? The other one is in a stair-like shape. The plate is in the form of a stair-like shape. Suppose This is of area A, the lower one, and it is divided into three parts. So its area is A by 3, A by 3 and A by 3. And this separation is B, suppose. This is B and this is B. So we are supposed to find out the equivalent capacitance between the points A and B. So think over it. So we'll proceed in a similar manner. So we need to find out the net capacitance between the points A and B. So let's try to solve it. So once again I repeat the question. It is a capacitor in which one of the plate is of area A, it's placed horizontally, right, in the form of plain sheet of negligible thickness. The other plate is in the form of a stair-like shape, as shown in the figure. And the separation is given by D, this separation. So this separation will be 2D and this separation will be 3D. Obviously, this separation would be twice D, while this separation would be equal to thrice D. We are supposed to find out the equivalent capacitance between the points A and B, right? So what to do is, a source or a potential difference is to be applied these 2 points. One plate will be at higher potential, the other one will be at lower potential. So what to do is, we'll just turn it through 90 degree. We'll just try to rotate it through 90 degree. So the diagram would be somewhat like this. Okay, the diagram would be somewhat like this. This will be the diagram. This is suppose point A, and let us consider this to be point B, right? This can be considered to be 3 capacitors connected in parallel. This can be considered to be a 1 capacitor. This is of capacitance C1. This can be considered to be of capacitor having capacitance C2, and this one can be considered to be of capacitance C3. Now look, why they are connected in parallel? Why we assume that they are connected in parallel? Because the plates of each of the capacitors are connected between the same 2 points A and B. So the potential difference across the plates of each of these 3 capacitors is same as that of the applied voltage across points A and B. That is, V is constant. So as a result, it is equivalent to 3 capacitors connected in parallel. So it is equivalent to this case. This is B. Suppose this is C1, this is C2, and this is C3. So what will be the net capacitance then? They are connected in parallel, so we'll make use of this particular formula, C1 plus C2 plus C3. Now let's try to solve it. Right? C1, this is C1. Now look, area is A by 3. Area is A by 3. And the separation is 3D. What's the formula, basic formula? That is epsilon A by D. This is the master formula, isn't it? For a capacitor having plate area A and the separation between the plates small d, then this is the formula for the capacitance of a parallel plate capacitor. So C1, this one, epsilon A, the area of each of the plate is A by 3. Divided by distance between the plates is 3D. Right? C2, epsilon, what is the area of each of the plate? Again A by 3. And what's the separation between these 2 plates? That is 2D. D plus D, that is 2D. This is D and this is D. Third one, epsilon, again area of each of the plate is A by 3. And what's the separation between them? It's D. Now we can easily evaluate it, right? Let's solve it and get the answer. So net capacitance, it will be given by epsilon A divided by D. And 3 can also be taken as common. Epsilon A divided by 3D, it's taken as common. So it will be 1 by 3 plus 1 by 2 plus 1. Let's solve it. Epsilon A divided by 3D, let's consider the LCM. 6, 2 plus 3 plus 6. 11 by 18, epsilon A by D. So this will be the net capacitance of this given capacitor. So students, I hope these questions are quite simple. You just need to understand the basic approach that is required in order to solve such questions, right? First, try to convert the given arrangement into a simplified circuit, right? And therefore, accordingly, you can apply the formula and get the result. So this was indeed a very interesting and very good question. Let's proceed with the next one. Okay. Next question is, suppose we consider a parallel plate capacitor. Each plate of area A and separation between them as small d. Separation between them as small d. This is it. It is given. It is a parallel plate capacitor. Each plate is of area A and the separation between them is given to be small d. Right? Now, the space between them, the space between the plates of the capacitor is filled with two different mediums of dielectric constants K1 and K2. And 50% of the space is filled with medium of dielectric constant K1, and the rest, that is remaining 50% of the space, is filled with another medium of dielectric constant K2. Right? So half the mediums are filled, half portion with medium of dielectric constant K1 and half portion of the space is filled with another medium of dielectric constant K2. Determine the equivalent capacitance. Determine the equivalent capacitance. Right? So we need to express the result in terms of K1, K2. A is given, separation is given. So two cases arises. There are two cases. Liquid can be filled in two ways. First is like this. It can be filled like this. This portion, it can be filled with K1 and the rest portion, it can be filled with portion K2. Right? So in this case, area would get halved while the separation will remain same. Clear? But on the other hand, the two liquids can be filled in this manner as well. In this manner as well. This is a medium of dielectric constant K1 and this is another medium of dielectric constant K2. Just observe the difference. Here the area of each of the plate will remain same, but the separation between them will get halved. It will be d by 2. Over here it will be d by 2. Clear? So these are the two feasible conditions. We need to explore all the possible cases, right? Okay, it is equivalent to two capacitors connected in parallel like this. This is suppose C1 and C2. So it is equivalent to two capacitors connected in parallel. Well, this one end-to-end connection. So it is equivalent to two capacitors connected in series. This is C1, this is C2. Suppose this is the point AB. Right? I hope it's pretty clear. Over here, since they are connected in parallel, so what will be the net capacitance? C1 plus C2. Over here, what will be the net capacitance? It is C net equals to C1 C2 divided by C1 plus C2. This has come from this formula. 1 by C net is equal to 1 by C1 plus 1 by C2. After evaluating, you will get this one. Now simply we need to substitute the value, right? Let's get it. Over here C1. Here C1 is this one. K1 epsilon. What is the area? A by 2. What is the separation? It is B. What about C2? It is K2. Whenever it is filled with, the space is filled with dielectric. So the capacitance becomes K times, right? So that is what I am using over here. C2. This capacitor, right? So it will be K2 epsilon. What is the area of this capacitor? A by 2. Area of the plates getting halved. While the separation of the plates remains same. B. So you can substitute this value over here. So we get, it can be considered to be parallel one. Right? What you get is K1 epsilon A by 2D plus K2 epsilon A by 2D. So we can consider epsilon A by 2D as common. So we get epsilon A divided by 2D as common and K1 plus K2. This is the net capacitance when the liquids of different dielectric constants are filled in this particular manner. I hope it's pretty clear. Right? Let's evaluate this one. Let's evaluate this one. What about C1 in this case? What about C1 in this case? It is K1, capacitance becomes K times dielectric constant times. Area of each of the plate remains same, A. Separation between them, it gets halved, D by 2. And what about C2? It is K2 epsilon A divided by D by 2. Right? So let's substitute the values over here. So what we get is, okay, we are solving it over here. So C net or C series, it is equal to C1 C2 divided by C1 plus C2. So let us substitute the values of C1 and C2 over here. What we get is, C1 is twice K1 epsilon A by D. C2 is twice K2 epsilon A by D. C1 C2 divided by C1 plus C2. So twice epsilon A by D, it can be taken as common. So we get K1 plus K2. Now let's solve it. Twice epsilon A by D, twice epsilon A by D get cancelled. So what is left is twice epsilon A by D. We are left with K1, K2 divided by K1 plus K2. Look, twice epsilon A by D, twice epsilon A by D. So we are left with twice K1, K2 epsilon A by D divided by K1 plus K2. This is the net capacitance in the second case. So this was again a very good question. So the net capacitance when the liquid is filled in this particular manner would be given by this. It is a series case. And when the two liquids are filled in this particular manner, then the net capacitance will be given by this particular case. Clear? So I hope such questions can be easily done. You should feel confident.